thank you, Adair, for that invitation, that introduction, and the invitation to be here. As Adair said, I've just recently joined the board of the Hanover Conservancy, and I've just been truly amazed by the work that this group does and the incredible staff that they have with Adair and Mary. So, this is the beginning for me of what I know will be a very long relationship with the Conservancy. And thank you all for your support of the good work that they're doing. What I want to talk about today is things like this picture and how this picture has anything to do with us here in New England, thousands and thousands of miles away. So what you're looking at is this is actually a photojournalist for National Geographic in a kayak on a lake. And obviously you can see there's ice and snow around it, but this lake is on top of the Greenland ice sheet. So this is, imagine a mile of ice underneath this lake. And you can see that this is actually pretty deep here. This is actually a tube that goes down through the entire ice sheet to the base. And eventually, this water will catastrophically drain out of this lake and go out into the ocean and contribute just a little bit to sea level rise. So that's one of the things we'll talk about today, sea level rise, but there's a couple other things that we can talk about in terms of how melting snow and ice in the polar regions actually affects us here in New England. And I'll just make sure this is working. So the context here, of course, is global warming. I hope I don't have to belabor this point at all, but we've got global warming. It's 100% real. We've warmed at least 2 degrees so far, global average. And not to go into too many details, but everything since around 1960, that's 100% human activities. It's not like human activities with some natural cycles. It is 100% human activities that have caused this. You can see just how crazy 2023 was, right? If there were no human activities, we would actually be very slightly cooling since around 1960. So what I'm showing here is if you run the best global climate computer models that we have, and you run them with no human activities whatsoever, you get this line here, which is flat, but it's actually slightly decreasing over the last 50 or so years. Versus if you run all the computer models with all human activities, you get this sort of mustard colored curve, and then what has actually happened is the black curve. So you can see that two things. One, our computer climate models actually do a pretty darn good job of getting reality correct. And two, as I said, everything since here is 100% human activities. And that's actually more than 100% because we should be cooling. So there are three big scale potential impacts that melting snow and ice in the polar regions can have on us here in New England. The first is that one I mentioned is raising sea level. We'll talk a little bit about raising sea level. The second is that it might actually change the jet stream. And you guys have probably heard about the jet stream. Anytime you watch the nightly weather forecast, talk about the jet stream. Around here, the jet stream is king for our weather, particularly in the spring, winter, and fall. In the summertime, doesn't play as much of a role. But for 3 of our 4 seasons, wherever the jet stream is, and whether it's north of us or south of us or on top of us, really determines our weather. So the jet stream is hugely important. And there's been a hypothesis out there for about the last 12 years that our jet stream is really changing, which really affects our weather here, and that changing snow and ice might be causing it. So we'll dig into that just a little bit. And the last one, which you may have heard about, Bill McKibben talks about this a lot, is that as the Arctic in particular starts warming up, or continues to warm up, and it's warming about 2, maybe even 3 times faster than the rest of the globe, the permafrost starts to melt, and there's a lot of CO2 frozen in the permafrost, and that releases more CO2 into the atmosphere and causes what we call a positive feedback, a self-reinforcing cycle. More CO2 gets released, makes it warmer, which melts more permafrost, releases more CO2, makes it warmer, right? I'm not going to talk about this one for a couple of reasons. One, it's not what I do. There are some amazing researchers at Dartmouth. Caitlin Hicks-Priest in the biology department comes to mind. This is her specialty. We should 100% have her come in to talk about this. 2, it's really uncertain, actually, what the effect is of this and how big it might be. And because of that, we need to do a lot more work on it because the scary projections are pretty scary and the not scary projections are pretty insignificant. So we really got to figure that out. So I'm going to focus on these 2 because this is what I do for my research. So I'm going to start by taking you to Alaska. I'm going to take you into Denali National Park on top of a mountain called Mount Hunter, which is right next to Mount McKinley. And we're going to zoom in here to a research camp that we've had for every year about for the past 15 years or so. This is a team sort of getting acclimatized. You have to get used to the high altitude. And then once you get used to the high altitude over about 2 weeks, you can use a helicopter to fly directly into the really high elevation research camp up around 13,000 feet elevation.
What elevation is this camp at?
This one is at 13,000 here. The other one was at about 6,000 base camp. So you can see what our camp looks like. We've got like an ice core drill tent, kitchen tents, and this is a time lapse showing how we actually drill an ice core, where we have a drill that goes down a hole and it collects about 3 feet of ice, comes up with 3 feet of ice, and we take that ice out of the cylinder, and then we put the drill back down the same hole and keep going down, down, down deeper until we get about 500 feet of ice or so. We then pack all that ice into these insulated boxes so that the ice doesn't melt. We helicopter it back down to base camp at around 6,000 feet. And then we can pack these boxes into ski planes. This is actually a snow runway on the glacier. We pack them into the ski planes, fly them out to base to Talkeetna, Alaska, put them on a freezer truck, bring them to my lab at Dartmouth College, and then we analyze them to try and figure out how the climate has changed for thousands of years. And that's my specialty, is looking at, say, the last 5,000 years before human activities, and then seeing that so-called hockey stick, like how we've transitioned into the human-controlled climate era. So here's another picture of that site at the top of Mount Hunter, 13,000 foot elevation. We can think of this as like Dartmouth's Denali campus. And it's amazing because we bring dozens and dozens of students up here. This is a great place to work with students because it's in a national park. They have a special team of climbing rangers who are like the best mountaineers you've ever met. And so if you get into trouble, there's help right there. There's also around 1,000 people every year who try and summit Mount McKinley. So there's a lot of infrastructure. There's 3 airlines that fly ski planes into base camp. So as far as like glacier research goes, pretty accessible. Nobody else goes here. Everyone else is going to Mount McKinley, which is just the next mountain over. So we have a nice remote spot here, but base camp is a really busy hub of activity during the climbing season when we're doing research there. This is Pat Saylor. He went, I think, 3 years in a row, and our climbing season is right now, May into June. And so he actually missed his graduation. And so we had a little graduation ceremony for him at base camp, which is pretty awesome. So one of the things that we can do with the ice cores is look at individual layers in the ice that indicate when it was above freezing for like an afternoon. So you can imagine this is a cold glacier. Most of the time it's below freezing, but occasionally we get a really warm afternoon and the top layer of snow melts. And that little bit of meltwater will trickle down into the underlying snow, which is still cold, and that meltwater will refreeze as a solid melt layer. And what you're looking at here is if you take one of these cylinders of ice, one of these ice cores, and you cut it in half. And so we're looking down on a cut half of the ice core. And you can imagine like time is going in this direction. So this would be older ice and this would be younger ice. And these layers here are those refrozen melt layers. They indicate an afternoon when it got above freezing, the meltwater trickled down and then refroze. This dark stuff is just normal snow that has not been affected by melt, but that just gets compacted under its own weight as more and more snow falls on top of it the next year. So we can tell the difference between these refrozen melt layers indicating warm afternoons and just the regular normal snow that doesn't have melt associated with it. So this is just one tiny little section of core for, out of the 500, 800 foot long core. So what we can do is use like photographic methods and actually measure the thickness, the frequency of these, even the darkness of them to figure out like how dense that melt layer is. And we can quantify all this. And for comparison, so this is a little snapshot of a core that represents 2009. This is a snapshot of a core that represents 1866. No melt layers. But we could do this for the entire core, right? Not just anecdotally me cherry picking a couple of spots. And so when we do that for the entire core, this is the year 1650 on the left, here's today on the right. And what each one of these dots represents is one of those layers. The color represents how intense it is. The size of the circle represents how thick the melt layer is. And you don't need to like get into the details except to see that basically back here in the 1700s, no melt layers. Had a few little blips here in the early 1800s, a few more in the early 1900s, and then lots and lots and lots and lots of melt in the last several decades. And so you can actually quantify this down here is what is shown, and this is work done by a PhD student of mine named Dom Winsky.
What does intensity mean?
So intensity would be, you have like a little bit of water coming down in versus a lot of water would be higher intensity. So it's like a more solid ice
Like a
layer,
warmer day.
be a warmer day.
What happened in 1790?
Good question. Warm afternoon, could have been a volcanic eruption with a little bit of dark ash on the snow surface. Could have just been a crazy warm afternoon.
Eric, can you remind me when the Little Ice Age was?
Yeah, so Little Ice Age around here is sort of this whole period, and it ends probably around 1850-ish. Like most of the glaciers reached their maximum extent in this area around 1850 and then started to retreat.
So if you go before this, do you pick up more melts?
So what's tricky about going before this is that the ice gets so compressed that it's hard to differentiate the melt from the non-melt. But we're working on ways to do it with like lasers and high-powered microscopes. So
How do you know that those melts are like an afternoon? Could they be like a week of warm weather or a month of warm weather? If it was, some of those things you should just show in that other slide were thicker
yeah,
than others.
so you're right. What it doesn't necessarily represent a single afternoon. But what we can do, so what Tom did was a whole lot of detailed comparisons between melt. We had a weather station up there. It was actually measuring the temperature every hour for 8 years. And so you can compare the melt that gets produced with the temperature and actually turn this into temperature and turn it into like a melt proxy record is what we call it. And so it might represent several afternoons in a row. It's always going to get below freezing at night, but it could represent like 4 afternoons consecutively that melted, and then you get a thicker layer. Another place that we go in your science department is to this glacier, the Athabasca Glacier. Maybe some of you have been there. It's like the most accessible glacier in North America. It's up near Calgary in Jasper National Park. And so this is a picture of the Athabasca in 2017. And we take a group of undergraduate students here every fall to teach them how to do this kind of research. It's called the STRETCH program. So here's some Dartmouth students we take them all the way up the glacier and put them right here at the ice fall and then take them through the ice fall. And so this is what the glacier looked like in 2017. And then this is what the glacier looked like in 1917. And what I've done is lined up these two photographs. We actually had students use this photograph and find this spot and take a duplicate picture in 2017 so that you can directly compare how the glacier has changed over that 100 years.
Is this when you used to be able to drive up to?
Yeah, you still can. So this is a parking lot right here, and you can actually walk up. You can walk up this path now, right up to the base of the glacier.
I was there in what would have been 77, and then have been back since, and.
So 77, it would have been probably right around here.
Yeah.
And there are little markers along this path showing you where it was in each year.
And then I've been back, and it's astounding how it changed.
I did this in 2017. I went back again last year. I'd been going every single year, and you notice the incremental change, right? But you go back 5 years later, and it's just breathtaking how much it changed. So this is what we were seeing in Denali, what we're seeing here in Athabasca is typical of these mountain glaciers, and they're all raising sea level, right? As this water melts off the ice, goes into the ocean, it's raising sea level. But if you really want to get a handle on the future threat of sea level rise and what's happening today, you got to go to the big elephants in the room, the biggest glaciers on our planet, Greenland and Antarctica. In Greenland, there's about 23 feet of sea level locked in the ice here. In Antarctica, it's over 200 feet of sea level locked in the ice. We're not equally worried about all parts of Antarctica. We're really worried about this part of Antarctica. We're also pretty worried about this part of Antarctica here. But this is the area that's getting a lot of focus. If you see anything in the news about the Doomsday Glacier, that's right here. Millions and millions and millions, probably $1 billion+ being spent researching that glacier in Antarctica. I've done a lot of research in Greenland. trying to understand how fast Greenland is melting today. And so what I'm showing here is a map of 2 different expeditions that we did in 2016 and 2017, where we were starting at this star, and at each one of these red dots, we collected an ice core. So we collected 16 ice cores total. In 1 year, we went from here all the way up to Summit, and then in year 2, we started at Summit and did this whole loop to collect the second half of the ice cores. Each one of these field seasons was about 6 weeks long. And so just to give you a sense of what this looks like, our question is sort of how fast is Greenland melting? This is what this looks like logistically. We were a team of 5, totally independent on snow machines, basically towing all the scientific equipment we needed, all the camping equipment we needed, all the safety equipment we needed. These are emergency pods in case we got stuck in a really bad storm that would destroy our tents, which does unfortunately happen from time to time. Didn't happen to us on this expedition, but it's happened on other ones that I've been on. So we had everything that we need. We're totally self-sufficient as we're driving across this entire route here, thousands of kilometers. So this is what this campus looks like. These are our individual sleeping tents. You get a tiny bit of privacy, get your own sleeping tent. Here's our communal kitchen tent. This is I love this picture because this sort of encapsulates all the various challenges that we have working in a place like Greenland. So I'm wearing cold weather gear, but we also have to do everything really cleanly because we're collecting the most pristine ice cores on the planet, and we have to bring them back to my lab where everything has to be super clean. So we have to have like the cleanest conditions even in the field. And so I'm wearing a clean Tyvek suit to make sure that none of the fleece and down and everything else I'm wearing gets into our samples. But we also have to worry about polar bears. So I've got a rifle slung over my shoulder, which is ridiculous, right? In a sense. But unfortunately, it's required by the Greenland government that we carry firearms at all times. We've never had to use it. And we would, if there was a bear around, you just leave. And when I mean leave, like get the helicopter to come and take you away, not walk away. You leave. It's only for like the most worst case possible scenario. But fortunately, we never have to use it. We do always have to have it. This is what it looks like from the sky. This was collected by a grad student using a kite, a camera on a kite. And so these are those same personal tents. Here's our communal kitchen tent. There's our science tent. There's our bathroom tent. And we do this for a reason, like line up all the tents in a row, because this is the direction that the wind comes from. And if you have the wind coming this way, then each tent gets drifted in by the other tent. These are things you learn after you set up your first camp on a glacier. You also learn, for example, don't park the snow machines like right behind the tents because then they get buried. The other thing we do is we always do our science upwind from our camp so that we don't contaminate, again, our sample. So this is where we're drilling our ice core several hundred yards upwind. And this is what it looks like. Here's 2 of my grad students, Karina and Gabe. This was a slightly more mobile drill than the one I showed you on Denali. Instead of a big honking drill, this is one that you can just power yourself. So Gabe is collecting about 3 feet of ice here, and Karina is analyzing an ice core that Gabe just pulled up before.
How deep are you going?
So in this one, we're going 30 meters, so around 100 feet. You can, with a drill this size, now we can even go like 50 meters, but it's a smaller
So you
scale
take them and
operation.
you put them in 5-foot sections, or what do you do?
About 3-foot sections,
Okay.
yeah, to transport them around.
And that's a lot of transporting.
It's a lot of transporting. It's a lot of lifting, a lot of digging. That's what we do.
So you put one set of tubes down, get the first one, put it up,
Yep.
and then you kind of like drilling the well, you get a second.
Yep, then you just keep going down the same hole and get the next 3
And
feet.
you keep getting longer and longer the thing you're pushing.
That's
And
right.
how long does it take to get all the way to 30 meters?
So with a team that knows what they're doing, you can do 30 meters in a day. That's a really big day.
A whole day?
Yeah, it's a solid day. It's an absolutely exhausting day, but you can do it in a day. And so if we look at the same sort of melt layers that I showed you for Denali, on a similar sort of plot, here's 500 years ago on the left, here's today, we can see a similar sort of story here in Greenland that we saw in Denali, where melting really accelerated here in the mid-90s, and that we're seeing melting rates that are much faster than we've seen for the last several hundred years. The other thing about this is that it takes an ice sheet a while to respond to climate change. So the warming that we're seeing here is sort of an accumulation, or the melting we're seeing here is an accumulation of the warming that was happening over these several decades. And so one way to think about this is like, in the mid-90s is when Greenland just started showing the warming that had accumulated before that. So it's really just getting warmed up now. And there are concerns about the ice sheets. The ice sheets are very difficult to stop melting once they start melting. You know, the classic analogy would be like a freight train, right? Really hard to stop once it's rolling. And there's a couple reasons why. First of all, they're massive. They're massive. Second of all, there are these positive feedback loops that I referred to when we were talking about permafrost. But there are different kinds of positive feedback. So in this case, the ice sheet is cold in part because it's high up, right? It's miles up into the atmosphere. And as you know, when you climb a mountain, it gets cold up there, right? So as the surface lowers with melting, it's lowering into warmer air. So you melt it a little, it's warmer, that makes it melt more, it makes it lower more, and it's warmer, and so on and so forth. Two is when you melt snow and ice, it gets darker. It actually physically gets like a darker color. You all know this, you go out, fresh snow, it's like blinding, you can barely open your eyes, you give it a couple days, not so bad. It's actually reflecting a lot less sunlight just 2 days later. Same thing happens as you melt it, it gets darker and darker, and that absorbs more sun, makes it melt faster. It's another positive feedback. The other thing that happens is that lake that I showed in that very first slide, this is what it looks like when it starts catastrophically draining down one of these holes, one of these mill wells or moulins down to the bottom of the glacier. That can actually decrease the resisting forces of the glacier. It helps the glacier to slide into the ocean faster. You can think of it, it's not quite the right analogy, but you can think of it as like lubricating the glacier as it goes down into the ocean. One thing that is like 100% certainty about melting ice, it is far easier to melt ice than it is to grow ice. When we look at the ice ages, it takes like 100,000 years to build up a whole ice age. It takes about 5,000 years to melt out of it.
Wow.
And that's because once you start these positive feedback cycles going, things can happen really quickly. And particularly when you mix liquid water with solid ice, things can happen really quickly. And I want to show you an example of that we experienced in 2012, which at that time was the warmest summer in Greenland. And so we were working here in an area called Thule. This is near Thule Air Force Base. And we encountered a lake. We were trying to study one of these lakes, actually. This is a helicopter image as we flew into camp on August 5th. And you can see this is the ice sheet right here. And then this is a lake right up against the ice sheet. And just to give you a sense of what it looks like on an aerial photo, here's that lake, and here's the ice sheet. We actually decided to check out this lake because it wasn't covered with ice, and we were going out on boats. So we set up our camp down here. And again, polar bears. So we had to have somebody awake at all times. We would take turns having polar bear watch. And the next morning, we started talking, and we were like, we all heard this really weird sound. It sounded like there was a new river. Like we knew there was this one little river, but it sounded like there was this rushing water. None of us could understand where it came from. A couple days later, we flew from here all the way up to here, passing by this lake again in the helicopter. And so this is what it looked like when we flew into camp on August 5th. And then 1 week later, this is what it looked like.
Oh my.
So here it is again before, and just you can look at this little peninsula here. And then here it is after. That's that same peninsula. You can see the two-tone line where the shoreline used to be. This just catastrophically drained, probably in the matter of hours, 6 to 12 hours-ish. The size of this lake, this whole lake basin is over 1 mile in circumference. All of these ice chunks collapsed down into now what was the empty lake basin. This is incredible. So this is the ice sheet. And what we think happened is the water was actually underneath it, melting out the bottom of the ice sheet. And then it found a path. It melted a path underneath the glacier all the way to the ocean, which is just outside the picture here. And once that conduit was made, whoosh, right? All the water drains out. That water was under high pressure and was actually buoying up this ice. And so this collapsed down. And when it collapsed down, it opened up these massive like canyon chasm cracks in the glacier. This lake drained, all this ice falls in. So I want to show you some helicopter footage that we took as we had seen it. We camped here for a few days, and then we asked the pilot to take us back over this site. We should have like publicized this. We were trying to get it published scientifically and figure out exactly how much meltwater and everything like that. And we couldn't get the proper data. We couldn't get good satellite imagery to actually capture the event. So we ended up not ever like publicizing this. But this is huge. Like the scale of this is really hard to express. We actually ended up really stupidly walking all the way out to the edge here just to try and get a sense of what's before we had this helicopter flight to really understand the scale of this thing. But it's massive. And so this is an example. You mix ice and water. Things happen fast. It's not just a slow linear process. You can have these non-linear, these really abrupt changes. And I've looked at satellite images since then. This is still there, right? This collapse feature, this massive hole in the ice sheet is still there. And so sea level is going up. So far it's gone up about 8 inches over the last century or so. The other thing to note is that it's accelerating in its rise. So whereas the early part of the 20th century, it was rising about 1/4 inch per decade, now we're at almost 1.5 inches per decade.
1.5 inches per decade, for every decade.
Yeah. The thing about sea level rise that I want you to understand, and it's not something that is, for whatever reason, talked about as much as I think it should be, it's fundamentally different than pretty much every other climate impact we talk about. It's different than temperature, it's different than precipitation and storms, which we'll talk about next. Sea level is its own thing. And the way you can demonstrate that, so this is a projection of past temperature and then future temperature under different CO2 scenarios. Really, really high CO2, which is actually not realistic anymore. We're not gonna do this, which is good news. But even these scenarios, right? Mid CO2 and low CO2 scenarios, temperature on this axis, more CO2, the more the temperature goes up. But notice, under these low CO2 scenarios, by the end of this century, the temperatures are starting to come back down. Okay, that's really important. Like, if we actually reduce carbon emissions, the temperature responds reasonably quickly. Sea level does not. It's really hard to stop these ice sheets once they start melting, and they started arguably in the mid-90s. Even under the most conservative, most aggressive CO2 reduction scenarios, which are also probably unrealistic, sea level continues to go up. And not just at the end of the century, it goes up for centuries, probably like 1,000 years. So this is like a forever problem. And I say that because I think a lot about working with communities and thinking about how do you become more resilient to climate change. And it's different from saying like, okay, we need to be resilient to rising seas for the next 50 years, which is probably what we need to do for temperatures, versus 500 years for sea level rise. The IPCC report has this dotted line. This is the latest IPCC from just a couple years ago. They have this crazy high sea level curve, which they call unlikely but possible. Really good news on this front. In the last like 2 years, research showing that this really is not possible. Good news. There
Is
is
this
good
chance or something we've done in the world?
Because scientists have dug into what caused this in some projections and figured out that that's not actually going to happen.
So it's not that we're doing anything better.
We are doing things better, but that's not why that changed. But this still remains. This is actual language in IPCC. Sea level is committed to rise for centuries to millennia and will remain elevated for thousands of years. And again, like that's not hot take news, but for whatever reason, that message doesn't really get out there, that sea level is like a fundamentally different challenge than the other ones we're facing in terms of how long we'll have to deal with it. And so what does this look like? It can look like this, so-called sunny day flooding, where it's just the high tide that didn't used to flood you, now floods you. It can look like this, so-called high water in Italy. It can look like this, sunny day flooding in Annapolis. And it can look like this. So this is king tide on our shoreline. There was an analysis done by First Street Foundation that found that we've already lost $15 million in property value in the New Hampshire seacoast. This is going to keep accelerating. Once insurance companies don't want to insure these properties anymore and those values go down, there's going to be like some threshold responses here in the real estate markets that you're just starting to get a hint of in certain places. So this is something we got to worry about. And the other time that we worry about it the most, of course, is during storms, nor'easters, hurricanes. This is a nor'easter from 2018. This is the #1 highest flood level for Boston. It beat out the famous Blizzard 77, which is now #2. An over $1 billion loss event, okay? And this is what that flooding looked like in 2018.
Wow.
So anything that's in blue here, like the picture in that last map was from right around here, right? This picture, this is near the aquarium and stuff, is right there, part of this blue.
Are we looking at slush, icy water? Is that what they?
No, the blue is just meant to show
No,
you.
in the photograph.
Oh, here? Yes, yeah, this is slushy, icy, horrible.
So it's like
Really
flooding
challenging water.
turned into slush.
Yeah, it was flooding on a really cold winter day, so it got pretty challenging pretty quickly. If you take that exact same storm, but have sea level rise for the next 50 years, and this is under a lower CO2 estimate. This is not some sort of like worst case scenario CO2, which I don't believe in showing anymore, because we're not doing it. But under a realistic lower CO2 estimate, that same event looks like this, right? So here is 2018 flooding, $1 billion of damage, and here's the same one in 2070, right? So this is the challenge, and this challenge doesn't
So downtown
go away.
Boston, everything but Beacon Hill.
Yep.
Yeah,
NOAA has a great website you can play with
yeah.
and look exactly what neighborhood's going to flood anywhere in the world.
And so the storms is the second thing I want to talk about with the jet stream, and then I'm happy to take questions. So this is a figure that came out about a decade ago now, showing the increase in the most extreme rainfall. What this means is take the rainfall event that happens like once, maybe twice a year. We're talking like 2 inches of rain in a day, right? The one that causes lots of flash flooding, causes problems. What this is saying is that in the Northeast, those biggest rainfall events are dumping 71% more rain than they used to. And we saw this, and we're like, really? That seems like a lot. So we dug into it and tried to study this in real detail over about the last decade now. And what we found was that they weren't wrong. Our number is a little lower than theirs. We came up with a 50% increase, and we figured out where their error came from. But a 50% increase in extreme rainfall is still a massive increase. And one of the interesting things we found is that it wasn't some sort of steady rise. It was a step change in 1996. I was just in a senior thesis presentations. We had 14 senior thesis presentations, Gary, last night. Probably a new record. And one of them was looking into this, and I was really pleased because they reproduced our results, came up with the same number.
Eric, was this when the Cold River flood happened? Wasn't it right around then?
Which one? Sorry.
Um,
Oh, 96?
Yeah, it was like right in that time period, the Cold
I
River
don't
flood,
know.
and then the one that took out Reservoir Road here,
The one that took out Reservoir Road was in,
2007?
That was
Yeah, it
when
was
Jason
5,
graduated. Yeah, it was
Okay.
it was,
2007.
was one of these.
Am I reading that right, that like that peak right there as it starts to get higher is 6.5 inches in one storm?
No, that would be 6.5 inches in 1 year associated with the biggest storms. It's a little confusing, but
You mean if you look at the biggest storms, they dump 6.5 inches?
yeah,
Okay.
something like that. And so, Hurricane Irene is a classic example of what we're talking about here and the damage that caused. What we decided to dig into is try and figure out, like, okay, so this happened, why? What caused this? What kinds of storms? Because there's lots of different kinds of storms that cause heavy rainfall around here. There's thunderstorms, there's nor'easters, there's hurricanes. So what was it? Which one? And what we found is that it turned out it was all three of them. It wasn't just one kind of storm. All three of them, all three of the kinds of storms that give us extreme rainfall are giving us more than they used to. So half of that jump up is from extreme rain associated with hurricanes, like Hurricane Irene. And we think that that's because the oceans are getting a lot warmer. That puts more water vapor into the atmosphere. And the atmosphere itself is warmer, so we can hold more water vapor, and it's like a bigger sponge. You can wring out that sponge, and more water comes out because it's bigger and it's got more water in it. And so you can look at something like this. This is in Texas, Hurricane Harvey. This is Houston in 2017. This is a $131 billion event, and with our climate models now, we can actually figure out like what the likelihood of this hurricane was without climate change and with it. And so climate change made this event 3 times more likely. That's pretty powerful to be able to say. In the past, we would just be able to like, oh, this is consistent with what we would expect from climate change, and do a bunch of arm waving and dancing around. But we can actually put numbers on it now. It's really amazing.
Are you saying it made the hurricanes more likely or the rain amounts?
It made the amount that fell here 3 times more likely
So you're more likely to get a hurricane, 3 times more likely to get a heavy rain.
to get that event.
Okay.
Then the other 40%
Yeah.
is associated with thunderstorms and nor'easters. So things like last July, 2023, things like July 1, like don't plan anything outdoors for July 1 around here. July 1 is this crazy day. I don't know why. July 1, 2013, 2017, it's don't plan things for July 1st. Big events. And so when we looked at these thunderstorms and nor'easters, we had a hypothesis that this was related to the jet stream getting wavier. And I'll explain why. What I mean by a wavier jet stream would be this yellow jet stream instead of a jet stream that looks like the red. A red one would be less wavy, the yellow is obviously wavier. The reason this matters is because when the jet stream is wavier, you're bringing colder air further down in contact with warmer air, right? You can imagine this is like the boundary between cold air on one side and warm air on the other. And that's when you get bigger storms. The wavier the jet stream, the bigger the storms. That's like a nice rule of thumb in meteorology. So that was our hypothesis, that the jet stream was getting wavier. And the cause of that, this has been a hypothesis that we didn't create ourselves. There's lots of other people talking about this. And the hypothesis is that the jet stream might be getting wavier because the Arctic is getting warmer a lot faster than the rest of the world. So what I'm showing here is temperature change over the last 100 years or so. The darker colors mean more warming, and as I mentioned, the Arctic's getting warmer about 2 to 3 times faster than the rest of the world. And so how that would work is that if this is your starting condition, and you got the equator is really warm and the North Pole is pretty cold, they're both getting warmer, but the North Pole is getting warmer faster, then there's a smaller difference between them, right? There's a lower gradient between them. And it's that temperature difference that gives you the strength of the jet stream and how much it wobbles and wiggles. So the hypothesis is that as this difference shrinks, the jet stream gets wobblier and wavier and could potentially create more extreme events. And a researcher out of Rutgers, Jennifer Francis, was the one who first really proposed this in 2012. So this hypothesis has only been out there for a decade or so. This caught on. Everyone loved this idea. Not everyone. A lot of people love this idea, myself included. It got associated with all sorts of publications out there. In 2011, we had this crazy winter with 2 feet of snow in New York, massive snowfall in Washington,
What is
D.C.
that picture?
That's like my favorite picture.
It's
It's 2 feet of snow in New York. A snow sculpture that some very clever people, it literally was 2 feet of snow though.
Why is it not do the opposite? I mean, if the gradient's less, I would think it would.
So, you know, it's a great question. So the way to think about it is think about a lasso. Okay, if you've got a lasso over your head, if you spin it faster, it's gonna be flatter. If you spin it slower, it's gonna get these big waves in it. The jet stream is the same way. If the jet stream is moving faster, it's flatter. If it's moving slower, you get the bigger waves in it.
And when it moves slower.
It moves
because of
slower when
less
there's less
differential-
difference in the
less
temperature.
differential To drive it.
Exactly right.
Article.
So this is all over the news. You probably heard of the fearsome polar vortex, right? In the winter, the polar vortex. And the hypothesis is that we're getting more of these polar vortex events because the jet stream is getting wavier because of climate change. This was tied to the massive February 2021 Texas storm and power outage, right? Winter storm causes Texas power outage, and climate change likely caused the storm. And the hypothesis again is that the jet stream's getting wavier, causing things like this. This is my favorite example of this. In Florida, when you have these polar vortexes, the iguanas get cold and they fall asleep and like hibernate and they fall out of trees and they hit you on the head. And it gets covered by the news every time. So we decided to dig into this, we being myself, and this is my laboratory manager, as a former student of mine. He decided to stick around and run my lab. His name is Jacob Chaliff. And we want to see, is this true? Like, is the jet stream actually getting wavier? as everyone says. And this is a hot take. Like, we're gonna publish this, we're gonna submit it for publication in a few weeks. The answer looks like no. The jet stream is not actually getting wavier. So we can see, what I'm showing here, sorry, is 100 years ago on the left, today is on the right. And this is several different data sets that all represent jet stream waviness. Jacob came up and created his own new metric of jet stream waviness. Super clever kid. And in this plot up here, anything that's high up is less wavy, down here is more wavy. So if you just ignore everything back here, it looks like, you know, a lot of the last 10, 15 years have been a pretty wavy jet stream. And a lot of the analyses that people do stop right here in like 1981. And so they see this and go, yeah, look, it's getting wavier and wavier. But what Jacob is able to show is that the waviness we're seeing lately is really not all that unusual compared to waviness we've seen previously. And in fact, there were lots of times where it was a lot more wavy jet stream than we have today. And we did not have Arctic amplification back here. So like literally as of this week, I'm thinking this might not be a thing.
So in 1980, we didn't have a barrage of storms, for instance.
Well, we did. Like the idea that a wavy jet stream causes lots of storms is 100% true. That is absolutely true. The idea that the jet stream is getting unusually wavy and it hasn't been this wavy in a long time because of climate change is not true. And it's really interesting, the bedfellows that this is creating. So like Texas ERCOT, the energy grid system, this is Texas, not like usually major proponents of climate change, but they like this because it lets them off the hook. To be able to say, well, the jet stream's getting wavy, it's not our fault. We built the grid, we built it right, but now the climate's doing this and it's not our fault. I actually got invited to an energy grid conference in Atlanta like a month ago, and they wanted me to talk about this, but they wanted me to say that the jet stream is getting wavier and wavier, they gotta be ready for this. And I wrote to them and said, hot take is, I don't think that's true. And they didn't want to hear from me. So I want to end you with two slides. I want to end you with some good news, okay? I am optimistic that we can improve things. A lot of what I talked about is some pretty depressing stuff, right? But two slides here to end on a high note. What I'm showing here is carbon emission in the future, okay? So carbon emissions in the past, and then everything in the color is in the future going out to the end of the century. These are these so-called like high carbon, high CO2, mid CO2, low CO2 scenarios. And you will still see lots of scientific talks that talk about the high CO2 scenario. This is not possible anymore. This is not gonna happen. And what's amazing is just 20, 30 years ago when I was a graduate student, like this is the path we were on, 100%. And a lot of work has been done in the last 30 or so years to make it so that we're not on this path, we're now on this path. That's huge. We want to get on this path, right? That's where if you want to reduce climate impacts, this is the path you'd like to get to. But our students, at least my students, still think we're on this path. And they know that we got to get here, and they're like, this is hopeless. But if they actually understand that we were here, now we're here, and yeah, we got more work to do, but we can do that. It's a different kind of message. And so I'm really fighting. This is still called the quote unquote business as usual scenario. It's not business as usual anymore. This is. This is if we just keep going as we are. So that's a really important message. Oh, and I hate this idea of like too late. Like we have 5 years to act before it's too late. Like really? If we don't act in 5 years, you're just giving up? Like there's no such thing as too late. No such thing as too late.
If we get Trump and it's a mess for 4 years, we can.
Then we will power on.
Keep working.
We will power on. I ain't giving up on my kids. There's no such thing as too late. The other thing is, I was getting pretty darn skeptical that the federal government could do anything in this, and I've really focused my efforts on local efforts. But there actually can be real incredible change. So this is US CO2 emissions. Well, most people don't know that the US emissions have actually been going down since around 2007. My students all think we're going up. We've been going down their entire lives. That's a nice thing for them to understand.
Well, what about the world?
Hot take on that in 1 sec.
Okay.
So we are actually been going down since 2007. This is where we were headed when the current administration took office January 2021. With one bill, the Inflation Reduction Act, we went from here to here. This is where we want to get to for net zero, but in one bill we did that.
Wow.
And this This green line would be what they wanted to originally do. Build Back Better, that like $3 trillion monstrosity. Basically, all the climate stuff that was in Build Back Better stayed into the IRA, the Inflation Reduction Act. One bill, huge difference. And what you asked, so what about the globe? So I'm sure you all saw the big news from New York today. And I'm not talking about the former president. I'm talking about Bloomberg. NEF came out and said, most likely last year was global peak carbon emissions.
Huh.
That's a huge freaking deal. Last year was probably peak emissions for our planet.
Who said this? I'm sorry.
This is Bloomberg. They have Bloomberg NEF is like their climate and energy forecast group. I really respect them and what they do. Huge deal if that's right. If it's not right, it's going to be like this year, next year. Like we're right there. So that's big. So here's my take-home
Somebody
messages.
Those are US projections, right?
This one was just US. What I was talking about Bloomberg though is full globe.
It's full blown.
Europe has been declining since 1979.
But I mean, then you
Right.
take into account China and Russia.
Yes, full globe. China is doing way more than we are right now. They're not the climate boogeyman everyone likes to make them out to be.
That's right.
Sea level is a forever problem. We got to think about it differently. We are seeing more extreme storms. Jury's out on the jet stream. If I had to be a betting man right now, I would say it's not because of the jet stream. It's probably just because it's getting warmer, the atmosphere holds more moisture, bigger sponge, okay? And we really are making progress. We need to accelerate it, but it's really important in my mind to like acknowledge the progress that has been made and certainly not lose hope. The thing that scares me the most is seeing like hopelessness in the next generation, like the students I have in my classroom now. That scares the crap out of me. So I've started really trying to make sure that they understand that real progress has been made and that there is a lot of reason for hope on this. So happy to take any questions about any of this or anything else you got in your mind with climate.
Eric, can you talk a little bit about, this is different than the jet stream, but there's been talk about the change in the ocean currents because of the
Yes.
warming
Meaning an inversion, right?
and how that
So-
could then affect our climate.
Yeah, that's a really interesting one. So what people mostly talk about when they talk about ocean currents is the Gulf Stream up the East Coast and then how much of that water sinks to the deep ocean just offshore Greenland, what we call the deep thermal handling, the deep water circulation system. We know that that has a big impact on climate over century to 1,000-year timescales. We also are pretty confident that that ocean system is slowing down. If any of you saw The Day After Tomorrow, the Hollywood movie about this, what happens when you slow it down is that less heat gets brought up to, say, Northern Europe. And so Northern Europe actually cools off a little bit. I might have a slide that actually shows it, but there's a,
I thought they cool off like disastrously.
yeah, well, see, that's Hollywood baloney.
Okay.
But it does cool off a little bit. And
What?
How many slides you got in there?
oh, dude, this is my job. This is what I do for a living. I'm trying to see if I've got one with the warming hole up there. So there actually has been a slowdown of warming over the north of, there it is. So you can see this little cold hole here. It's like the one place on the globe that's cooling down. It's because the Gulf Stream is slowing down. It's bringing less heat up the coast. And if that continues, this cool blob could expand and include bits of Western Europe, the UK, Scandinavia, and make their warming less dramatic. Probably not actually cause cooling, but certainly could be a place that's less warming than the rest of the globe into the future. Long term, what does that mean for climate change? Probably not much. I don't think we're going to screw up the ocean circulation system long enough for it to have the kind of impacts that we see when we look at like the last ice age. There are like these big shifts in climate that last thousands of years that we think are associated with this.
What's in the middle of Africa?
No data.
Same here.
And in the Amazon, no data. Gary?
Yeah, with the sensitivity now that we have for satellite-based altimetry,
Yeah.
what do you see in glacial rebound in a place like specifically Greenland, but maybe also Antarctica, I'm not sure about that, but Greenland, you know, they're talking micrometers that they can analyze now. So, do you see this? Do you know this data?
Yeah, I do. So what Gary's talking about is that as you melt ice is really heavy. As you melt it, the ground starts lifting up a little bit because there's less weight on it, right? So the ice is pushing the Earth's surface down, and as you melt it, it comes back up. And so you can see, particularly in Southeast Alaska, some pretty high uplift rates of the ground and actually local sea level lowering. Certainly that's the case around the coast of Greenland here as well. Where we are, this is actually a sea level rise hotspot on the East Coast because of the opposite problem, because the forebulge is still decaying. So
Because
yeah, I know. That was for Gary, but then I'll explain it for everyone. The last ice age covered all of Canada in an ice sheet, and it went all the way down to Long Island. Okay, and that pushed down the Earth's crust all over Canada. Underneath the surface of the Earth, underneath the crust is a slushy layer, and that slushy layer, when you push it down, goes out to the sides and actually buoys up the crust just outside of it. So the crust was pushed down here, and that caused it to lift up just to the south. When the ice melted, the reverse happens. The crust here lifts up, and the crust down here comes back down, and that's still happening today. So the ground underneath our feet is slowly sinking still because 14,000 years ago, the ice sheet melted around here. And so what that means is that our sea level along the whole East Coast here is rising about twice as fast as those global average sea levels that I showed you.
Sinking in the Earth.
Because the Earth is actually sinking as the ocean's rising.
But would isostatic rebound in Greenland affect then what is happening with the?
It affects it really minor, like here.
Yeah.
It doesn't, it affects us in a tiny amount.
But up there.
But up there, yeah, up there, their sea level is actually falling as the ground lifts up quickly.
Right, okay.
Yeah, so when we talk about sea level rise, we're usually talking about the global average sea level rise. But what's happening in any one particular location can be quite different from that.
So
And the
what
extreme
happens as you
version
go
is where it's
down
actually lower.
to like Florida then?
Or New
there's not
Orleans.
much of that, there's no rebound issue.
So Florida is actually pretty stable. It looks pretty much like the global average. New Orleans is sinking for a different reason, and that's because it's on a whole bunch of mud that's just literally 10, 12 miles thick, and they're pulling out oil, and they're pulling out groundwater, so the whole thing is sinking really
It's
quickly.
like Arizona.
Will Antarctic see the same thing as ice melts? Will that land go up?
Yeah, and you probably can see that today. I'm not 100% sure, but you can probably see it on the Antarctic Peninsula today, where they've seen a lot of melting. Antarctica down here, you know, the so-called Doomsday Glacier is like just now starting to get going, and I don't know if we can see that in the uplift data yet. I don't
So
think I've
how
seen
is-
an Antarctic data.
How
set.
is that measured? I mean, is it satellite, LiDAR stuff that is happening? Or?
So most of the time, what you're doing with that is you actually have, to get really good measurements, you have like a concrete foundation, like the base of, imagine the base of a statue, and then you have like the most powerful GPS unit you can make, and you just leave it there for years. And you just watch that signal slowly rise or slowly sink. And so we have those all over the globe. And actually a faculty member in our department in neuroscience, Bob Hawley, he's in charge of the whole network of them up in Greenland that Gary's talking about.
Who funds those things?
You do.
Good.
Thank you very much.
Yeah,
The US
wonderful.
taxpayers.
I mean, we should be funding things like
Yeah.
gauge data and rivers. And,
It is. So it's all US taxpayer dollars funneled through organizations like NASA, like the National Science Foundation, and like the National Oceanic and Atmospheric Administration, NOAA. Yeah.
Is your information offering any hope about stabilizing the rise in ocean temperatures? Because there's such a huge heat sink.
Yeah, you know, the rise in ocean temperatures is kind of nuts this year. I don't know if you guys have seen any of the coverage in the New York Times. It's off the chart. I'm trying to think if I had it open earlier today. I wouldn't have been in that one. Yeah, it's really remarkable. The ocean is taking up a lot of our extra heat from greenhouse gases.
And the carbon dioxide.
Yeah, so the heat that the CO2 is trapping, a lot of that's going into the ocean. The ocean has got a huge thermal capacity. To be honest, the ocean warming in the last like 12 to 15 months has been so large that it's not my specialty, but what I'm reading about is that folks are still trying to figure out exactly what's going on. Part of the story is that we had a big El Nino event, but that's not the whole story.
A big
because
what, you mean?
El Nino last winter.
Yep.
But that's not the whole story because El Nino is only in the Pacific and we see this in the Atlantic as well. So yeah, it's a really interesting, the ocean temperatures from like a pure scientific perspective right now is interesting because we don't fully understand, we can't fully explain everything we're seeing and how quickly they've warmed just in the last year or so. Most likely, there's some internal variability going on and it'll sort of settle back down. I mean, it's definitely getting warmer, don't get me wrong. But like, usually when we see something off the charts that we're like, whoa, what's going on? It comes back to some sort of less extreme, confusing level soon thereafter. I remember 2007 going to our big conference in California that we have every December. And the September sea ice data had just come out and it was mind-blowing how much 2007 had dropped below the overall trend, and people were going like, oh my goodness, we're on a new trend now. And fortunately it was not. The next year it came back up. It's still a crazy, scary trend, don't get me wrong, but it wasn't a trend that we could not explain. I'll say it like that. Yeah.
Yeah, well, I've been going over on the coast of Maine for many years since I was a kid and used to have property right on the water. And now, fortunately, our property is inland. Last January, there's some really big storms over there.
Yeah.
And I anticipated, and there was a lot of damage, a lot of people's houses. I'm just talking, there was also wharfs and things, but I'm talking about what's now very expensive property on the water. And people are spending thousands and thousands of dollars bringing in rocks to reinforce that. And to me, it was kind of a wake-up call. I'd been anticipating it, but I was thinking it was going to be a hurricane. This was not a hurricane. It was it was high wind event coupled with high tide, as I understand it.
And it wasn't even that big of a storm. It wasn't like a storm of the century.
It wasn't that big of a storm. And it's sort of like, it's just going to happen again. I mean, so it's inevitable, right? Particularly because of the sea level rise.
Yeah, this is
it
the
all
pattern
along
we
the
see.
mid-coast or where are you talking?
Yeah, mid-coast I'm talking about. Yeah.
This is the pattern you see, like the flooding that you used to only get with the crazy storm of the century, you now get because of, up the biggest storm of the year maybe, or maybe not even, but you link it with high tide and just get some bad timing and combine it with sea level rise and you can get, that was now the #1 highest flood level for that part of the coastline.
But people are spending on fairly small properties, $20,000, $30,000, $40,000, $50,000 to bring in rocks.
And if you have the
But
money
they
to
said
do
there
it,
was a rock that was moved at Pembroke Point, 775 tons. I mean, and just see some of these rocks that are moved. I mean, the power of it is unbelievable.
yeah.
Wow. That blew me away. And I have to say, can you say again what was announced today in New York? Who announced it?
Yep.
Because I nearly burst into tears when you said that.
Yes, so Bloomberg, NEF, I'm actually not sure what NEF stands for. That is their sort of climate and energy research subgroup. They released a report today that said that most likely 2023 was our peak carbon emissions for the globe. We've been decelerating, and now we should from here on out be decreasing.
On that note, thank you so much.
Thanks.
Wow.